Says we're recording. Hi, this is Bob. I got a neat little thing here, and it just involves magnets and other natural forces such as centrifugal and momentum. But what we have here, I'll take one at a time. This is a string. It's actually a fishing line. This is a magnet on the end, and right now it's just set up as a pendulum. As you can see, I'll bring it up. You can see that it's just suspended from a boom, and it works just fine. And then in this whole CD case, as you can see, it's my magnet's attracted to it. That is because inside of it I have suspended or propped up a magnet, another magnet. This is a toroid magnet. It's, if you don't know what a toroid is, that's unfamiliar to you, just think of it as a donut. It's an old ceramic magnet out of an old microwave. And I've got it set up because I've played with this thing. Anyways, the neat thing is that I'm going to show you. First thing, you got to try and get this. Hold on. Right underneath the boom, as close as you can, as best as you can figure out. It's hard to but you can see when you get. Now remember, the shape of the feud of the toroid or the donut is also the same shape. It's a donut shape. So you can see how it pulls when you get outside. But right in the very center, there's equal forces, so it acts, it just hangs there. Now, as you get closer, it diverts, you see. And if you use it as a pendulum, whoop, I'm too close. I guess I'm too close. Yeah, well, something changed. It's hitting my, I've got it so close that it's hitting the edge of the CD case. I don't think that'll affect what I want to show you. Now, the neat thing is, it's on this is a fishing line actually, the string, and I'm going to orbit this magnet. I'm going to make it orbit and watch what happens. I'm going to get it started. Whoops, it starts out elliptical, but it'll round itself out. And goes faster and faster as it diminishes. But there's something that it's doing. It's not only rotating around the magnet. See it spin now? And it'll bobble around and wind up. Winds up, stores energy in the fishing line in a twisting form, as we call it. It's like a torque. It adds up torque in the line. The reason it can do that is because the two magnets are attracting each other, and as this goes around, it locks in, as you can see even in my hand. See how for every revolution around, the magnet in my hand turns one revolution. And that causes to build up energy in the fishing line or the line. See if I can do it again. And I'm not getting, well, there. See, and it's winding the string up right now. It's storing energy in a string, and when it gets so far, there, now it's releasing it. and then it'll torque the other way for a while. But each time is less and less. It's using up all the stored energy until it returns to zero. I can only go so far because then I hit the support strings holding up the boom. There. And that was a good start. See, I don't know if the camera's picking that up, but it is actually the magnet that's moving is rotating one turn for every revolution it goes around the toroid magnet. And it gets faster. Now, right now, it's kind of an elliptical orbit. You can, if you're lucky, you can get it started where it's pretty circle. But it turns into a pretty true circle toward the end. You see how it gets faster and faster as it gets closer and closer. And it's still turning now. It's releasing all the energy. And there it goes. And I think that's kind of neat because it poses a question that's kind of interesting. Oh, I got it elliptical. The question I have is, does the energy to get this started equal to, less than, or more than the energy stored in this twisted string? The energy that's applied, that is being applied to the suspension string or the fishing line. And you can get it to work a lot smoother. It's a thing you can play with, but it's kind of interesting. Now, the question, like I said, the question being, is the energy being put into the string, and now it's being released, is that equal to, greater than, or less than the energy that was required to start it? It goes back and forth until it finally uses up all the energy and the magnet tries to get to an equilibrium, which it can't, by the way. I've got it too close to the magnet. You see how it stays affected, but if I raise it like that, you see how it'll stay I don't have to go much. You see how that moves over, and then you just pick it up and it settles right in. But I get a better twisting action the closer I can get it. And so that's why I've done it that way. There. Do it one more time. And it doesn't matter which way you start the pendulum action. And you have centrifugal force and gravity. And everything that's happening here can be expressed mathematically. Like the energy to get it started, which would be I'm part of the experiment because I'm supplying the initial energy. Now, how many calories I burn, I would think you would use those terms. How much energy did I use to get it started versus the amount of energy that's stored in the pendulum, in the string. And it's a twisting torque type energy that it releases after it stops because the torque, it stops twisting because the torque force overcomes the magnetic force. But you can see how strong that is. See, I'm just holding it out. So I've got these are pretty strong magnets. Now I'm going to just rotate the other way. See, I started out at elliptical orbit, but it'll straighten itself out. It's just a fun thing to play with. And like I said, the question that I keep asking is, does the energy stored in the string in the form of a torque, the twisting action, and it twists so far, and then it releases it, is that greater, equal to, or less than the energy that I used to get it started? It's just a fun thing to contemplate. If you're a real mathematician and you can work out all the formulas necessary to calculate that, you can come up with an answer. It appears just off the top that it's actually got more energy than what it took, but I can't verify that because I don't know how much energy I'm using to get it started. I would think with the laws of conservation of energy, whoa, there, I did it that time. Anyways, I would think with the conservation of energy principle, which we all live with, that it's the equal. So that it's kind of interesting, but just looking at it, you'd think it would take me more physical energy to wind the spring up or the string up to store energy into the twisting of the string than it would be for me to just simply reach over, pull it out, and then give it a little push. And that's really all I'm doing. And the magnets and the centrifugal force and gravity and all this is now in play. And there you have it. And it's winding that spring up because the magnet is in, I call it in step with the two fields are in step, so that's causing the magnet on the pendulum to rotate one revolution for every orbit around the toroid magnet or the donut. And there you see, you can do this. This is just, it's kind of I don't know, it's not really a paradox, but are you gaining usable force, or are you just building up the maximum energy used to produce it in the first place? And the only energy I use to produce it is me, the operator. I have to reach out, and we'll let it quit doing its thing. Anyways, this kind of just, it's not electrostatics, and it's just magnetism and centrifugal force and momentum force and radial force and torque, twisting force. And that's how it works. And it'll do that until the torque or the energy stored in the string is so strong that it'll stop that from circling. And when it stops it from circling, it stops it from spinning. I mean, it does. It stops the spinning. And now it's in this sort of, I call it the center neutral zone, and it just goes the opposite way. So it's kind of a fun thing. See, and it'll work. The fields are locked in step, which is what's causing the, come on you, I'm having a terrible time going this way. There we go. It's kind of an elliptical thing, but it'll straighten. But it works. You'd think it's pushing it away, but and it does. But it'll straighten it. It'll grab it. Finally, that takes over. And it's winding up the storing energy into the string. And once the string gets enough torque in it, and it pulls it to a stop in the center, and allowing the energy in the string to be released. Hey, I just thought you kind of, people that like to play with magnets, I thought this is a neat thing. I kind of discovered it by accident because I was doing another thing. I play with magnets from time to time, like I said earlier. This is a lot of fun now. Well, all right. I'm going to let you think on that, and if you can try to figure it out, have fun. Bye.